Morning, everyone. Welcome. You can hear me okay? Yeah, I see a thumbs up in the back, so that's a good sign. I would like to start this evening by recognizing that we gather on the traditional, unceded, and unsurrendered territory of the Algonquin and Anishinaabe people. We honor the rich history of the Anishinaabe people and work to include and celebrate Indigenous knowledge and stories in our library collections and services. And as we look out the windows, even though it's dark, we know where the Ottawa River is and where Algonquin families used to live. And we strive to provide opportunities to learn together as we journey towards truth and reconciliation. Thank you for coming this evening. That's the way I will start, and I'm going to pass it over to Mike, co-host for our series.
So welcome everyone to the third seminar in our series for Inquisitive Minds. I look around the audience here and I know that some of you have heard what I'm about to say. Some of you may not. Please bear with me and laugh at the appropriate spots. The series is born out of the observation that there are places in this town where people who are doing interesting things get a chance to show off and tell people what they're doing. For example, we look at the art here. The authors have meetings, the children have meetings, but the people who are doing things of scientific interest do not have a platform. So the idea behind this series is to give them a platform. And the reason I'm repeating this every one of these lectures or seminars is because we're always looking for people who are doing interesting things. And I know this room is full of people who are doing interesting things, and I'm already planning, or I've targeted people for next year. However, I would also like to point out that we still have 2 vacancies in the schedule. December is open, and the rules are, if you're doing something interesting, we encourage details, we encourage equations, and very limited requirement is you must be able to have the potential to draw an audience of at least 1, and that is to retain an audience of at least 1. So if anybody here is doing something interesting and thinks they can draw an audience 3 days before Christmas, please speak to myself or Naomi. We also have May is available. Again, the competition will be black flies and mosquitoes. So there's, again, if you want to say something this year, please let us know. Otherwise, I'm preparing for next year. I think that's pretty much the introduction that I want to give. Oh yes, I should just summarize for you what we have arranged. It's an eclectic collection of material and topics. We started off with Steve Dion on forest fires. Is that now on the, okay, it will be on the library website. We did manage to record that. Is today's lecture being recorded? Okay, today's lecture will be recorded and will be on the library website. Unfortunately, we did not manage to record Charles Backer's talk. The next one after this will be Dave Winfield talking about a history of the slow-poke reactor and small reactors, followed by Alistair Miller, who tell us all about the hydrogen economy, followed by Stephen Douglas, who will talk about backgammon and the mathematics behind it. And then we end up the year, unless somebody volunteers for May, Ruben Marini will talk about how to build a battery backup system for your house. I think that gives everybody an idea of what this series is all about. And again, I encourage people who are thinking about saying something to please contact us. Just a few matters of of comfort after the lecture is over. There will be coffee and cookies, and I encourage everyone to stick around and discuss what you have just heard. And we are doing an experiment. There will be a voluntary exit fee where you can express your appreciation for the speaker. There'll be a collection box at the door, and you can put anything you want. The money will go to the food bank, and I can report that we've already enriched the food bank from the first two lectures by about $200. I've had a quick look at Bill Diamond's first slide, and he will start off by telling you what he has done that would qualify him to talk on this topic, so I'm not going to introduce him in that respect. But I would like to make the important point that he was thinking about these things 30 years ago at just the right time for AACL to cancel all accelerator projects and all deep scientific, fundamental scientific work. So he left it, but he has not given up on it. He's published a paper 30 years later, just recently in Applied Physics Journal, discussing what he's going to talk to us tonight. And this is all very appropriate time to be thinking about this, because AACL, which is, some of you may know that this town is sort of entwined with that institution, is talking about producing medical isotopes from an accelerator, which is far different than anything that they've ever done before. So, Bill, I'm sorry to have taken so much time.
I need to get used to holding the mic somewhere near me. So, start off by giving you a little bit of a hint of where and how I've been in the last 50 years. I got my PhD from Toronto in nuclear physics in 1974. My advisor was Ted Litherland, who was an alumnus from the 50s and 60s here, early 60s. I think at that point, basically, he said, there really isn't going to be a very exciting career in nuclear physics, so he aimed me towards accelerator physics, and that's where I ended up at Chalk River in 74 and 75 in accelerator physics. Then there was one of those periods when there was no jobs at Chalk River, so I ended up going down to Columbia University for the next couple of years on super postdoc, which actually it had a little more benefits than postdoc, but not a lot. And eventually I got my first job at 32 with a scientist at Schlumberger Doe, coming up with ideas to measure things in the bottom of an oil well. We actually built a electron linac that went 10,000 feet down into the earth and made the density measurements. And by that point, cost of oil, most of you here will remember oil prices going up into the 30 hours, which is probably equivalent to 150 or 200 in today's money. So Schlumberger spent a lot of money on ideas then, and the oil went back down to $12 or $13 a barrel, and everything was shown. So I'm used to things being shut down on me. And I went there. From there, I went to be a senior scientist and built the front end of a $300 million accelerator at CBAF that was down in Newport News. And then got a call back from John Hardy to come back to Chalk River in 89, then worked on the task facilities until the fateful time that Mike mentioned there, when they decided there was no more interest in that. And so then I pretended to be a reactor development R&D type for the next 12 years to get my pension in, and then I went back to do some interesting work. I'll get these out. Okay, so we'll do a little bit of basic understanding of what these things are. On the left-hand side, there's the periodic table, which I'm sure everybody in here spent some time looking at during their high school chemistry. So that's sort of an array of how to lay things out. It mainly aims at the chemical properties of the elements. But you can see the various the vertical lines on there. They basically are a group that's all similar characteristics all the way down. Just while it's here, just the one thing now, their radium, which I'll be talking about later, sitting at the bottom of group 2, and obviously, because of that location, it's a pretty reactive material. So forget about it for now, for the next little while. And over on the other side, where we have the chart of the nuclides, which is somewhat more complex, but it basically lays out in the same way, a method of actually looking at all the isotopes. And somewhere down in the center of that, on the center of all that, there's a little bit of a black wiggly line that gets up to about here. Everything else that isn't on that black line is radioactive. So radioactive substance, well, any non-stable nuclei in the chart of nuclei, so that's 3,000 or so. Then again, a random process that leaves the nucleus more stable. And one or more decays eventually leads to the black line of stability, characterized by decay modes and half-lives. Two that are fairly common modes, which are of interest in the medical isotope game, is beta decay, which a neutron ejects an electron, changes to a proton, and positron decay, in which the proton ejects a positive electron, called a positron, and it changes into a neutron. So this gives us kind of an interesting approach of how we get to the isotopes of interest from the various methods of doing it. First thing over, the little one up here, this little section here, what does no carrier added mean? That's a commonly used term in medical isotopes. And it basically means no carrier added. This means the preparation of a radioactive isotope, which is essentially free from stable isotopes of the same element. You're basically using sub-nanograms in a lot of cases. So you don't really want it to be parts of that as being the stable isotope, which is just filling in spots that you would otherwise rather have a radioactive isotope. So we look at a little chunk, just any chunk of the periodic table here. You will, the table of the isotopes. If we start from N and Z, then that's the stable target material. We can then shift various methods. We can change that to a radioactive isotope of interest. If you look along this, if you're going east and west along that line, you basically can't produce a non-periodic because you're still with the same Z. So what one has to do is get up or down from that line. So the various approaches, the reactor, you get mostly the fission isotopes, and that's especially true of Tech-99. There are N gamma, which is that just goes that way, that goes east-west. NP is much lower cross section, but it does give you some useful isotopes, and even more on the lower cross sections are the NPN reactions that gets you down in this little corner. The cyclotron produced isotopes are by far and away the most common method of producing medical isotopes at this point. That one, you start with your NZ, and proton takes you up one. There's P gamma occasionally, yes, but it's much lower cross section. So you start removing neutrons, you get Pn and P2n. If you're higher energy, P3n. If you get lots of energy, then you get P many n's. And a lot of these are where the useful isotopes that are used for medical work come from. And fairly recent one is to go use electron accelerators, which Mike mentioned I was talking about in '95. You get a gamma ray in and it knocks a neutron out or two neutrons out. That's again going east-west. So what you need to do at that point is to, okay, still working, yeah. Cheap product. We'll go back to what Mike brought back for me. Back in the old days. Yeah. There are reasonably good cross sections to Z up to 40 or 50, where you get a gamma ray in, you go down a proton and a neutron. Those are some very useful isotopes we produced in that group there. My one equation for you, Mike. Yeah, basic rate of, I'm standing on my own foot. the rate of production of these isotopes is basically a linear product of the cross section of the flux and the number of target atoms and time, of course. Now, as that's being built up in a linear fashion, the term like this is actually decaying it. So that one has its shape is basically like that. And after 2 or 3 half-lives, you're basically running near saturation, and you can go as long as you want after 5, and you're basically decaying as fast as you're producing. And as soon as you stop doing the actual irradiation in whatever way you're doing it, then you start decaying. And so that's the main method. So if you've got a reactor, you would like a very high flux reactor. When you're talking about accelerators, it's typically lots of protons or lots and lots of electrons because cross sections are lower. Now, this is 10 or 12 years old at least, because I haven't been able to find a nice modern slide that's done in the same way. And this gives sort of a chart of the nucleides from the perspective of one of the most interesting medicine. And you'll see on here, the giant black things in the center of it is Tech-99, which still represents the order of 70–75% of the isotopes used even to this day and age. And then you get some large ones down here, the positron emitters, and iodine, a couple of iodine isotopes, xenon isotope. There's a series in here, and then you get a few up here. And at this point in time, this one is growing significantly because this is actually being developed as a drug that will actually fight cancer as compared to just showing you where it is. But that's sort of the basic map of what's being produced. And so the nuclear medicine itself, branch of medicine that provides information about the functioning of specific organs or treats some diseases. Diagnostic procedures are routine, as I just mentioned, about 80,000 procedures a day in North America, and still most of them are with tech. There are several 100,000 plus, no, 200,000 in the world, and many, many, many cameras. Therapeutic procedures, these are becoming more interesting, as basically you're using a radioactive isotope. You tag it with something that actually carries it into a cancer, and when it decays, the energy of decay, which is typically a beta or an Auger electron, and the modern stuff that we're getting into now is using targeted alphas. A lot of energy is deposited in tens or hundreds of microns, maybe a millimeter or two, and destroys a cancer cell itself and tends to with the right setup, you don't just do too much damage to healthy cells. And at this point in time, its use is much lower than the diagnostics, because diagnostics are much easier, but it's growing in importance, and it's got a lot more commercial value than the former. So, typical example of a non-diagnostic, everybody in this room, I'm sure, has had an X-ray or two in their life. Nuclear diagnostics, the branch that uses nuclear radiation to study internal organs. You substitute a radioactive atom or isotope for the same non-active isotope in a compound that seeks a specific body site. And of course, an easy one is iodine seeking the thyroid. The radiation source is taken internally. The patient is scanned with a bit of tomography, CT scanner, the very sophisticated detector that does a full, completely circles the patient and scans. And one of the big advantages of that is that you have the capability of any dynamic measurement. You can actually see blood flow, or you can see where an area is concentrating in. If you get various things like PET isotopes like glucose that hang around where there's cancer because there's a high uptake of glucose. So these are very important medical procedures. Two types of diagnostic scans. SPECT, which is the common one, that's basically single photon emission computed tomography. That's where the MOE 99, Tech 99 isotope was used mainly. And then positron emission tomography. And that uses the fact that when a positron decays, it combines, the positron wanders around until it gets down to thermal energy. It combines with an electron and produces two 511 kilovolt gamma rays exactly at 180 degrees. So when you measure a coincidence in a detector over here and a detector over there, you know pretty much really quite accurately. And some of the modern PET images are just spectacular with their resolution. And what they're doing in some of the things now is combining a PET isotope with a therapeutic isotope so that you actually can see exactly where the thing is getting together, where it's decaying. So that's called theragnostic. So that's a term that's just coming into use nowadays. Popularity of the spectrum. Well, the reason there's 70% is just mainly right there. Cost of the scanner is low, the staffing requirements are low. Tech 99 bonds with many substances, so they don't go to the heart, they don't go to the bloodstream, they don't go to many different organs. So it has a lot of values. And the real one that's still important is the apparent isotope on 99 has been exceptionally low price for a generation now. We at NRU and NRX produce so much of that. I don't know. I really don't know how much of the total world use in the last 50 years, but I suspect it's 20% or something. That scanning is the reactors are starting to get old, not too many more. So it led to a decade-long effort to use acceleration to produce MOE 99, which I'll talk about in a few minutes. I deem that largely a failure at this point, but there's some nice new facilities developed and basically proved that it would work, but it just never competed with cheap MOE. The PET requirements are a little bit more complex. You need a cyclotron at the hospital to begin with, so you've got anywhere from 5 or 6 million up to many, many more million than that. Accelerator and shielded rooms and then you've got to have a radio pharmacy to take the product from there. You need staff to operate the thing, staff to handle that. And your scanner is significantly more expensive because it's more detectors and a lot more complex electronics in it. But you get a high quality, much higher quality image at a lot higher cost per scan. So those are the two basic nuclear diagnostic measurements. And as I say, there are a lot of them. And can't help but say, stopping for a minute to talk about the reactor-produced MOE 99 because it still dominates the whole field of nuclear medicine. Basically, we radiate U-235 in a reactor somewhere and it produces MOE 99 is statistically about 6% of all fissions, and so you get quite a high fraction of things. And then the big factor with that, the really super factor, is once you do that, you separate that, and you put MOE 99 on an extremely convenient device. I mean, that basically, you know, it's easily picked up by one person. It's probably 30 or 40 pounds of lead. In the center of it, you have an alumina column, which the MOE 99 is on. You throw a bit of saline solution through that, suck it up into an evacuated vial, and that picks up the Tech 99 and all the MOE sticks on the column. And you pull it out, you use half a dozen scans in various places, and you let it build up for 24 hours, and you just take it out again and start all over the process. And so that can be used for often 1.5 to 2 weeks before you, depending on how big the charge was to begin with. So you've got this very, very convenient method to do many, many scans with one of these. And then at that point, you send it back to the whoever's doing it and get a new one and you start all over again. That convenience is, you know, it's just hard to overlook that convenience. I just stuck this on the bottom though to sort of indicate, you know, I think it was an article that was a little more financially oriented than fitness, physics, and medicine. But Tech 99 has become a trivially low-priced commodity, with there being no correlation between market price and the true cost of production. That's been true for years and years and years. Well, what about accelerators? Okay. And as the accelerators started to become available in the 40s and up through 80s and 90s, even through 90s, there was an awful lot of work in underlying nuclear physics. And a lot of accelerators were built during that stretch. Parasitic research on those on medicine was used to study medical isotopes, but there was really not any possibility of getting any meaningful anything more than research, because they didn't have the capability. And I was using those accelerators in the 70s up for 6, 7, 8 years in there. And my personal recollection on them is most of it was you're lucky to get a 3-day operation on an accelerator. If you got 50% of it, you were doing well. So they weren't particularly reliable. So one needed dedicated and reliable accelerators to provide medical isotopes. And that led to production of dedicated medical cyclotrons. And but really 70s, 80s, 90s, there's about 6 or so different manufacturers produce cyclotrons, and there were over 1,000 cyclotrons sold for that purpose during that stretch, and they still continue to sell a lot. So I've read this. This is quite a good article from. I looked through that and went back and started looking into it. This is the what we call the first medical cyclotron, and basically. Lawrence, he had 2 smaller cyclotrons before that. I think he invented them in the mid-30s or 34. I'm probably wrong, but in that region. By this point, he got one big enough that it was using, I think, 20 MeV or so, and so he was able to start doing producing isotopes in a meaningful fashion. So that's, I think, kind of an interesting first started that. It's actually sort of almost 10 years ahead of getting medical isotopes from reactors. So we had a pretty early start. Just an aside like that, I think this is a Tim Antea that I used to know back in the time I was working at Task. He was at Michigan State in the cyclotron. The reason I mentioned that is because in the next one, personal note on that, the article credits Henry Glosser of Michigan State as the inventor of the cyclotron, but he didn't start. We already had the work of Chalk River was 2 or 3 years ahead of Glosser, at least. And by 74, when I was here on postdoc, there was already a team of 6, 7, 8 people working with John Obrod, actually building the first, putting the research together to do the superconducting cyclotron. So I mean, that's one of the statements from the first superconducting built, whatever it was. And the other one here is a total of 9 superconducting cyclotrons were built for heavy ion science in 81. All of these machines are still operating and almost blah, blah, blah. But no, our cyclotron was shut down and demolished for steel scrap in 97. You notice on here, and I couldn't find another picture, so I had to put my own mugshot in on this. But there's our task plate that was basically, it was opened in 1986. And as you see, 11 years later, we fully met all the goals that we should have met about 3 years before that. So we had maybe 3 years of operating, but it actually was doing what it was supposed to do. And then we shut it down. So I thought that, a little bit of personal feeling there, shall I say. Now we look at a typical modern isotope cyclotron. These are GE ones. A lot of these are raw. They're basically small enough that they fit in the basements of many hospitals, and they're self-shielded. So you close the door and there's enough iron shielding. I don't think this is, but a lot of them have enough shielding around them that you don't need to build a large concrete bunker to put the thing in. It's basically shielded within its own steel walls. And so these type will be used somewhere in a hospital. They'll produce the fluorine-18 PET isotope, and that then, you know, gets then taken. I mean, actually, there's a full chemistry. You see it's up along the side here. A lot of that is part of the chemistry kit that you actually take the target material, which is usually fluorine-18 water. I mean, or 18 water, I should say. So you do a oxygen 18. It goes P into fluorine-19, neutron out, and you get fluorine-18, and that's the positron emitter. That's by far and away the most used positron emitter. So the target will be moved from there into something over here, and a lot of it will be basically processed, you know, very close to it, or else they're at a room right adjacent to it. So it's basically automated. Because you've only got a less than 2 hour half-life, so you've got to basically get it out of the thing and process it and get it all out of the way before the couple of hours are out. What about electron accelerators? My interest, I've been working on them off and on since 78, 77. Oh, yeah, 70. When I came out the Chalk River on postdoc, 74, 75, I was working on electron accelerators at that point. So it's been around. I've been part of my career for many years. Many low energy accelerators, because I mean, literally thousands of them are used for sterilization and cross-linking of polymers and things of that nature. But it's only the last 15 or so years that the commercial electron accelerators with the energy and power to produce medical isotopes have become available, and there's still only a few of them. Greater challenge is to use in a reactor or a cyclotron, and there's still only a few of them under development or in use. And I'm thinking, you know, realistically, especially when we see the next section on how Rolling 99 was such a roaring success, that probably their main value remains in the production as targeted alpha therapy or therapeutic isotopes such as copper-67. Copper-67 is a quite upcoming thing. Is basically copper can be made into a lot of compounds that will basically be accepted by various parts of the body. It decays with fairly low energy betas, which produce the therapeutic effect. And it's also got low energy gamma rays of a couple 150 or so kilovolts. So you can use it with a SPEC scanner and you can see where it is. And if you really want to get sophisticated, you combine some copper-64 with it. And that's a positron emitter. So you can then get precise images of where you're fighting the death, you know, where it is and what it's doing. So electron accelerators are by far the best way to produce it. It's not easy to do it with photons. So this sort of gives one an interesting look at it from the point of view of things. IAEA produces these interesting documents, tech docs or technical reports. You can see I'm not even sure the one at the top there. That may not be the earliest. The manual for reactor-produced isotopes goes back to 66. And these documents, they go through, you know, there might be 20 different isotopes in there. There are about 8 to 10 pages on each one showing how to make a target, how to irradiate the target, what processes are needed to get the medical isotope out of interest. And so if you put good documents, then you can see in 2000 and 2010 a whole series of these technical reports coming out on cyclotron work. And down at the bottom, there is TechDoc. I don't know. I'm a co-author on it. I finished my work a year and a half ago. Should I make your comment, James, about IAE? Yeah. Anyway, Jim's comments to me when I was talking about that, he says, you asked how many people work at IAEA, and the answer was about 10%. So that's there, and you know, this was a year and a half ago, and I haven't had any feedback from them in over a year. So eventually that'll be out. But that gives you, in a sense, that gives you an interesting snapshot of how these various processes have developed. Typical accelerators, This is the one that's out in Saskatoon that's producing copper-67 right now. That was Mark Dion, who a number of you in here will probably know fairly well because he was here for many years before he moved out to the light source. And that's the newest of the machines in there. That's a real beefy thing, 50 MeV electrons and 100 kilowatts. So that's a very powerful accelerator. Again, one last comment on personal history, because this is about the time. And back in the summer of 1995, John Hardy gave me and a couple of Herman, and I think Helena, we all were tasked was, if the accelerator was working well and you had time, think about what we could do to produce a new facility at a task that could produce radioactive ion beams. What the idea was is you produced radioactive ion beams actually in an ion source. Then you ionize them and accelerated them through the heavy ion accelerators, and the nuclear physics available with radioactive ion beams just opened the field immensely. And there's been a lot of major new facilities built since that time. But I was looking around and using my background. I had some background in fission. I had a lot of background in accelerators, and that I put together the idea of using photo-fission of a uranium target to produce neutron-deficient heavy ions that could be accelerated in task. And from that, I made the obvious step of going to photonuclear reaction on MOE 99. That's just the heading of a little short technical note I wrote at the time, which I think that may be the only copy left. Anyway, it was the idea of using MOE 99 from a high-power electron LINAC. But 1 year later, task and accelerator physics was shut down, and one had to go to work on the myth of 10 and 10 or somewhere else. So I stayed on the myth of 10 and 10. But I did have an invited talk down in Oak Ridge because several of the people from task went down to Oak Ridge, and I got an invite down there. Again, there was no way that someone from Chalk River was going to go down as an official host of Chalk River and talk about physics. So I had to take vacation and go down, but eventually they convinced me to get off my ass and write it up. So I spent weekends writing that paper up, and I ended up with according to Google, I have over 100 citations. I have no idea. But there have been quite a few new facilities built, including at Triumph, who a few years after we were closed, we're building that facility that I said we should build. So anyway, and my thoughts at the time, someone will build this. It's too good of an idea, but not going to be Chalk River. So unfortunately, I was quite quiescent. But so much for my personal part. I've got my little grease in here. Jump forward to 2010 after the shutdown of NRU and shortages of MOE 99. Government initiated an expert review panel, and after a number of months, they came up with invest in alternate non-reactor based technologies. Completely sensible one, get better use of Tech 99 because they weren't using it for 24 hours. They were just using it, and then when it's down overnight, it was decaying. So I started adding shifts, off-hour shifts, and getting a lot better use of Tech 99. They age expeditiously in the replacement of NRU. And key consideration, don't put any more funds in the maple. So that was in 2010. The response, non-reactor isotope supply program, called NISP. It's announced in 2010. Program supported research, development, and demonstration of cyclotrons and linear accelerator-based production. No mention of reactors. And as you can see, it was not exactly overwhelming the amount of funding. 35 million over 2 years, and you didn't actually get that was funded for April, but the funds didn't show up until December, so that there's only 18 months or 17 months of actual funding, and only 10 million of that went for the electron accelerator. So it was not a lot, but at least it gave us a start. So this is what I did. I worked after I retired with Mark Dion, who out in Saskatoon, and basically, how do you produce MOE 99 with an electron accelerator? Well, you start with electrons But electrons have real lousy cross sections. So you have to produce photons called bremsstrahlung. And then the bremsstrahlung interact with the target. And then you get a gamma N. And what I'm showing here is cross sections. And you can see on this side here is about 150 millibar. And you'll see when I get into a few photon lines that this is fairly low cross section. And what you have to do to come up with yields is you basically have to integrate the curve for the production of bremsstrahlung. So if you start with a 35 MeV electron, you get nothing at this energy, and you just keep getting more and more as you get down to the low energy end. The region where this curve overlaps this curve, basically the integral of that gives you how much actual isotope you get. And this sort of shows one of the Monte Carlo codes, a visual. The electron beams coming here in blue. This shows only the high energy ones. You can see it's over 10 MeV photons you need, so it's really very high energy photons. This shows only the high energy photons, so they're mostly produced in a forward cone, but as you can see, it keeps going all the way up. There's some going backward, but not very many. And the target has to be somewhere just beyond that. Now, this was my early attempt at producing it. I didn't do a very good job because the target was too far beyond the bremsstrahlung converter. But anyway, there's what the facility looked like. It was built in a target room at the end of the synchrotron light source. It was one that had been used 40 years earlier, back in the early days of a small LINAC there. Some of the real key players at Saskatoon at that point did electron scattering. But that room had sat empty for ages, so we had to fit it all in a very small room. I mean, that length there is about 10 feet, and that's about 7 or 8 feet. So you're talking about 20 feet by 15 feet wide, and you're putting in something that's got the bremsstrahlung flux when we're running at 35 kilowatts is higher than the gamma ray flux in the middle of a reactor. So it's very, very intense gamma ray flux. This shows one early 3D model of what we built. Where are they now? We had original goals. Yields were about as predicted, but because it was different than the generators used to produce Tech 99, Health Canada was insisting on a whole new set of tests, far too costly for a small group like Mark. So the work ended basically, I think, 2 or 3 years. I might not quite have these dates right, but in that time, I think it was in the middle of the early part of the COVID, so it's somewhere back there. He switched to Copper 67, where he had a lot less regulatory issues, and there was a demand for the product, and they paid more than a few bucks a curie. So these are some images in a paper that he put out, and just that's where that ended. Cyclotron production, there was a lot more work went into that. That basically, you're only getting Tech 99, so you basically only have 6 hours, so you don't have a great, you don't have the convenience of distribution that you have with Moly 99, but it's basically proton comes in, hits the Moly 100 isotope, the same as we used in the gamma phase, but it goes to Tech 101 and decays from 2 neutrons to Tech 99. Much, much lower cross section. You can see on here again, this is the energy of the protons, and the cross sections, Tech 99 M is up there. So it's not all that much higher, 250 or so. But you do get an awful lot of Tech 99 ground, so you get a lot more of that than you do when you're decaying from a fission product. And right to one end, to Moly 99, as you can see, it's hardly worth worrying about. So you basically have to produce Tech 99M. And then you work their way through. There's cyclotron produced tech was approved by Health Canada with work from the Triumph was pushing for many years. In December of 2020, I spent some time looking, but I didn't really find much indication there's been any significant acceptance in Canada of it. But they did get 4 to 6 new facilities funded, though, which is way better than the poor electron people. There's a new one in Vancouver, a new one in Saskatoon, which is the one that AECL is proposing to work with now in the production of targeted isotopes. new one in Thunder Bay, a new one in St. John's, and I'm almost certain somewhere in this collection there's another one. And Calgary is supposed to be opening a new one next year. So there was I don't think there's a lot of Tech 99 being produced by cyclotrons, but I think there's an awful lot more cyclotrons than we used to have, which is not a bad thing. There are a lot of other good uses, but the cyclotrons being funded for that were way more expensive than the ones, like a PE tech, something, the 16 MeV, 15 MeV, 100 microamp. These new machines are 19 to 24 MeV and almost a milliamp, two beams at 400 or 500 microamps coming out of them. So they are far more costly than needed. I mean, the facility they built in Vancouver, I think, was 24 million, I think I read, and I think the one in Saskatoon was in a similar range. I mean, there's a lot there. There's the cyclotron, there's all the labs, there's all the good health spec stuff, all the QA work. So there's a lot of stuff to it, but they're very pricey facilities. I say, program largely a failure. Reactor moly is too cheap. In the US, Northstar invested 100 million, with about 50 of it coming from the US DOE program to get rid of HEU. Literally, just a few weeks ago, October 9th of this year, Northstar, which has already got two 100 kilowatt accelerators already operational to do it, canceled the program. This SNNI, some Society of Nuclear Medicine, something or other, said that it didn't appear to be any shortage of material. Northstar completed the construction and installed the new equipment in 22, and I think they had announced that they'd actually gotten to 100 kilowatts on some target. And yeah, the company's involved in the program, that it works. And I think that's true. All the various things with the research that went on for those 10 years, basically all achieved the goals that they set out to achieve. So it's functionally works, but as I say, it functionally worked, but I think the fundamental problem comes down to this: you can't compete with cheap tech, and these generators are so much. The moly produced from any of the accelerator approaches is high or low specific activity, so it's curies per gram, whereas the stuff produced in fission is thousands of curies per milligram typically. So it's orders and orders and orders of magnitude different. So on a little column in here, you may have a fraction of a milligram or even less, and it's got a lot of tech stored on it. But there's one other potential that may also be part of it. There's let's see if I just can't speak there. Anyway, there's a neutron capture work being produced by Babcock and Wilcox using the Bruce reactors, and they're irradiating natural moly. So there's a whole suite of 6 or 7 isotopes. So target material is real cheap. They said his favorite discussion: non-proprietary aspects of the neutron capture, moly isotope generator, and technical development of a proprietary generator. So they're basically claiming that they have a generator that's the same sort of small size as the one you use for fission moly. And so in terms of the footprints, it's designed as a replacement. And in September 22, this is the latest thing I could find, submitted a new drug application to the FDA for approval of this particular thing. So it may also be that this has the competition and the accelerator games worried. I mean, something like a Bruce reactor, that isn't going to shut down anytime soon, and these things basically run forever with shut down every, I don't know, 18, 24 months or something like that. So they just keep going. And flux in them, or according to this article, the flux, whether you're radiating it, it's about 2 times 10 to the 14th. So that's up with most research reactors. So if it works the way they claim, then it's a pretty good approach. Now we'll shift into look at the big item, the one that where everybody's talking about now is targeted alpha therapy. A lot of recent work on that. You produce short half-life alpha emitters. You tag them to carriers that deliver them to cancer cells, And the alphas, which only go 50 to 100 microns, are a very short distance, few cell distance or less, basically deliver a very large amount of energy in that short distance. So they kill everything that's in that region. Only a few potential alpha emitters that can be detected. Most are challenging. And actinium-225 is one of the most attractive candidates. So have a quick look at where we are on that technology right now. We get electron and proton accelerators both seem to have a fairly important role in that. And just to say, these targeted alphas now are probably the most interesting area of medical isotopes by a significant amount. But right now, there's a small source. There's a small source in this Chalk River. There's one in Oak Ridge. There's one in Germany, and there's presumably one in Russia that we don't know much about anymore. But you basically start with uranium-233, which we produced in large quantities in 50s and 60s for as a potential atomic bomb material, only to find out that its spontaneous fission rate was too high and it tended to be detrimental to trying to use it as a bomb. So, but anyway, there was a lot of it made and it's still in storage. But yeah, so what the problem with that was that you can only process small amounts at one time, and it leads to quite a limited source of actinium-225. After 60 years of decay, a kilogram is still only producing a few microfarads, so it takes a lot. The relation of 232 is it's a way that's actually quite likely to be successful, but it requires a high energy accelerator, sort of 100 MeV or higher. So there's a couple of isotope accelerators in the States. We have Triumph in Canada, and all of these things are fairly high demand accelerators. And there's also question of, can any of these be used on a routine basis to reliably produce, X number of curies every month, 12 months of the year, with backup somewhere? And I think the answer is probably no. But there's the other challenge. I mean, there's 50 times higher fission cross section, so you're producing a large amount of material that you have to get rid of. And it also produces a lot of actinium-226 and 227, which you can't separate from 225. And the 227 has a 20-year half-life, so you don't really want that decaying in your body for the next 20 or 50 years of your life or whatever. So there is a small cross section going directly to radium-225, which then decays to actinium-225, but it's much smaller than going to the actinium-225 directly. So it's a method. The target is not messy. It's just thorium. It's very easy to use it as a target material, but you've got these various challenges. So now we go back where we were talking, the very beginning of radium-220. Radium was used basically from soon after Marie Curie found it in, I think, the late 1895, 1896 time frame. By the time you get into the beginning of the 20th century, they were already proposing uses of that to use for curing cancer. And for the first 50 years of the 20th century, that was sort of the major medical isotope. Now we're coming back to it now because we need it to produce these isotopes of hydrogen, because it's the only semi-stable material that is in an area where it decays with a series of short half-life alphas. So we have these multiple reactions here. There's the first one is a fun one. I'll show you in a second. Beta, or 3 neutrons, 2 betas. So it's a series of staggered decays. Eventually goes down to this, which is the same thorium-229 that they were using from the uranium-233. That thorium-229 is an 8,000-year half-life. So it takes a lot of it to get to produce a useful amount of the 10 or 20-day isotopes. You can get from the radium-226 with an N2N reaction, but that's a particle reaction, so it requires sort of 6 MeV and higher. We don't have many reactors that do that. The thermal reactors have almost no flux at that energy. And then you can get into the P2N reaction using one standard medical cyclotron and gamma N again with it produces radium-225, which then beta decays to actinium-225. One of the advantages of that is that once you've done your initial irradiation, you can then do first separation, and then there's any 227 in it, you clean it out at that point, and then your next separations will be basically producing very high purity actinium-225, which is the desired product. But this one's a fun one. You start with the radium-226 target in the hyper reactor, where you've got some of the highest neutron fluxes in the world. So it's got a pretty decent cross section going over radium-227, only a short half-life, so it basically almost immediately goes to actinium-227, which has got a very large cross section going over to actinium-228 and a very short half-life here. So that goes up this way, and more neutrons, high cross sections, and you get to where you want to go. Turns out, though, at the end, you still have a lot of that left. And what the first TAT isotope has been medical approved by the FDA is actually a radium-223 compound produced by this decaying to that, which decays to here, and then that is actually used for some sort of Zyglo or something like that. It's a Bayer's isotope, but it's used for bone pain and bone cancers because radium is a natural bone seeker. So that's the first one. I think that was almost serendipitous, I suspect. That just gives you an idea of the buildup in that very high flux from that reactor. You know, 30 days of irradiation at 1 gram, and you're still only up to 10 milligrams, and you know, 5 grams of thorium to produce a purity. So it's not exactly interesting way. It's fun physics. It makes some lovely measurements. So that basically, this is basically challenges of using radium as a target. It's everything from here on in is dealing with the proton accelerators or electron accelerators. And everything is challenges or how you produce targets with radium and how do you handle targets with radium. So you can see there's 5 alphas from the radium-226 decay, 4 from the actinium-225, and there's also co-produced 224 with 4 more alphas. So you can get large numbers of alphas, and alphas are alphas for a short time, but they very quickly decay and pick up some electrons, and they become helium atoms interdispersed all throughout the target material. And I don't know if we really know very much whether it remains interstitial or whether it becomes gaseous helium. But the guess is that there's all these little needles that were made for cancer, 75 years ago, and there's significant numbers of those leak. So that's a tendency to forget that. And they're in an iridium or platinum encasing. So something had enough pressure in there to blow the thing apart. So what suggests that there certainly is a lot of the helium are coming out as gaseous helium and not as interstitial locations. So that's a 10-day irradiation, you're ending up with a lot of cubic millimeters inside that target. Whether it's 24 millimeters cubed of real helium or whether it's a number less than that, anyway, the potential for very serious problems there. And then you get to the metal itself, highly reactive. I mentioned at the beginning, it's on that particular group 2 where it's quite reactive, lousy melting point and thermal conductivities. And the radium compounds, the various salts and stuff like that, nitrates and chlorates and things that you might want to use. Most of those, I don't think the thermal properties are known. You just have to work with barium analogs and hope that things are remain about the same, or at least follow the sort of general trends to get you to barium. So that's sort of thing. And then you've got the target material itself. It starts up here. Its first decay product is radon gas, which our radon gas we have in the houses and stuff like that. Well, if you've got a gram of radium, that was basically the standard. The old standard for radioactive decay was a gram of radium was a curie, which is 37 gigamegavolts, or 3.7 times 10 to the 10th disintegrations a second. It's also, if you take a gram of radium, you look at it from the point of view of just gamma ray emission, not even looking at the betas and alphas, it's but are 1.5 hour per hour at a meter from it. So you've got to do all your handling. It's got to be behind substantial shields. You can't use a thin hot cell. You've got to work with something that's beefy. So there's that to begin with. But then the first decay goes to radon-222, which is a noble gas and a reasonable half-life. So that is not easily trapped. And especially in accident scenarios, you have this can be float just about anywhere, wherever you have a target damage or anything. And when it decays, then it eventually goes down real quickly to here. But you're hitting lead-210 at 22 years. So now you've got a something that will potentially stick to any surface that where actually the final decay happens. And you've got a low level of alpha contamination that'll last you for years and years. So that means you've got a real bloody mess to clean the thing up. So it's not a very nice target to work with. So basic proton target, if you put just a piece, you somehow or other sticks radium onto a backing, probably a copper backing. You got to have ways to get good connection between that. It's got to stay because you've got to cool it through the copper piece. You got to get the heat that's coming from the front end. It's got to go all the way through the target material. So there's challenge to that, and you've got to add a protective foil because there's all that radon that's coming off that, and if you don't contain it within that protective foil, then it goes right out into your cyclotron vacuum system. And that's never a good idea. So there's challenges with that. I was going to draw another picture, but my design program crap there on these. Such as you use a slanted target to reduce the target thickness, and but as you take something that's this thick normally, and now you're approaching it like that, it's now 10 times thicker, but so is that thin layer you want to protect it. It's 10 times thicker. That in turn is absorbing the power from the protons going into it, and you've got to transfer all that through the radium. So it helps, but it's not a magic solution. My co-author of the paper that Mike mentioned was Carl Ross, who retired from NRC back in 2014, I think it was. He's a real Monte Carlo specialist. So this is just a basic, that's basically an infinitely thick target. And basically we radiate it for 10 days with lots and lots of protons, because I was looking to see if there's any activity at 227, and there wasn't. But you get activity at 224. That's this big one here, way higher than the 225. And then there's some 226. And you can see half-life of 224 is only a few hours. But what that does is decays to radium-224, which is about 3 or 4 days, and decays with very high energy gamma rays, and then 225. And so you can see, again, there's even more helium when you look at it like this than my last thing. You're getting the order of, from that particular run, you get something like, well, I think that 37 was after I only took 0.4. I assumed that on a thin target, only 40% would stay in the target. The alphas would go right through the target if you're on any sort of slant distance. So that's a very crude number, but give or take, there's a lot of helium in there that has to be gotten rid of. So some comments on this approach. The plus side, the cyclotron production is well established. Cyclotron, you can get cyclotrons in probably 18 months for the purchase order going in. The shielded buildings you build up are fairly well established. You can probably find somebody who will do your safety analysis for you. And there's the potentials of very high yields. And you can find operations, people with good operations experience. You can probably bribe them to leave what they're doing and come to you if you've got a good, interesting project to work on. But this approach has been reported on for well over 10 years. I think it's more closer to 20 right now. Only limited progress reported. It requires significant radiation protection resources just because of the type of target. And that's true. I mean, most of these things apply to electron too. There's been at least one major cleanup required in Germany where a target got damaged and it contaminated the cyclotrons. And target damage leads to large quantities of mobile. When that decays, what do you do with a target chamber that's contaminated with 20-year half-life? Do do you clean it? Do you replace it? You know, a target chamber is a couple 100,000 probably. So it's not something you want to do without considering the various options. So the high yields come with substantial helium production, only a thin protective layer. And likely, I don't really know, but I'm guessing metallic radium is the only target option. I don't think you can get away with using salts in this if you want a moderately thick target, because you got a high softening power of proton. So if you want to get a modestly high yield, you're probably stuck with using a metallic radium target. Now we look at electron productions. Again, we got the accelerators are available. Reaction cross section. There's the again. What one has to be aware of in most of these calculations. In the previous one on the protons, there was 4 experimental points. Everything else was model. On this, there are no experimental points. It's basically all model calculations. So you have to be aware that what you get from these model calculations have to be treated with some suspicion, because the models can be off by a factor of 2 in worst cases. So, but those are the cross sections that one gets from fluid calculations. Cross sections are lower, but much higher beam power is available. And you've got the stopping power. That's basically how much energy you lose per linear distance of, MeV per millimeter or MeV for whatever. That's, or 1 MeV per gram per centimeter squared for electrons compared to 13 for protons. So you're talking, less than 10%, which means the electrons will travel quite a bit farther, and that obviously allows you to go through multiple windows without too much absorption losses. And typical setup uses a converter and then uses the hydrogen Bremsstrahlung to produce deuterium-1. So this is the paper. I just quoted an example of a target design from this paper Carl and I produced in January 2021. In that case, we produced a design that included 1011 Bremsstrahlung converter and 2 targets of radium, all in one unit. The whole works of this is extracted at once. You basically throw the tantalum into a corner and let it decay for a while and use it somewhere down the line. And you take the targets. Now, the only trouble with this, you have only a single window between here and your accelerator vacuum. So if you lose a window, you've got again, the possibility of serious contamination. So that was what my thoughts were a few years ago. Since then, they've gone, I'm getting late enough. I won't worry too much about that. But when we produce, look at this. So when you produce reactions that produce radium-225, we want actinium-225. So this shows, again, the calculation for what we had in our paper basically is the buildup of radium-225 with time, and then the accelerator is turned off here in 10 days, and it decays away. All the time that this is being built up, you're getting decay to actinium-225, and turns out when you do the math, it's somewhere between anywhere in this region here, it comes to an optimum before it starts going down. So you can pull one off here, and then you can pull it off again somewhere around here, and you can do it another time later. You can probably do 3 or 4 meltings of this to still get useful quantities of activity. You got to look at that for these targeted alpha isotopes. The typical treatment dose is the fraction of a millicurie. So if you're getting a curie of the stuff coming out in your thing, you've got quantities enough to do hundreds, if not fraction of 1,000, a big fraction of 1,000 possible treatments. So it's not like where you need 20 millicuries from Tech 99 to produce 1 treatment. Much less. So your a few curies is actually quite a large amount of this. Now, one other option you've got, which is quite a valuable option, because you don't know, there may very well be actinium-227 produced in this. There may actually been some radium-228 produced in this part of the original radium, because it's in these decay processes. That's also part of one of the decay chains. So you may have actinium-227 you want to get rid of. So if you wait shortly after irradiation, if you just do a separation, the actinium-225, you may want to use it for something, but it's not going to be used for medical studies. But you also take care of all the actinium-227. And so then when you start to build up, you've got a very pure product, and probably the purest of any approach. So that has a certain advantage in that sense. And now, where my present thoughts are on this, much more conservative. They now put a couple of windows and separate water-cooled titanium windows and separate the vacuum of the accelerator completely from all the target activity, and then produce a cute little. This is called the converter target, and I've designed this to have 6 slots in it. And initially, I would use 6 tantalum. At that point, the yields are going to be significantly lower because you're absorbing a lot of the high-energy photons in the latter parts of these. But what it really does is it reduces the amount of power in these 2 radium targets to a very, very low amount. And so at that point, it opens options. You can use things, like radium oxide if it exists, radium nitrate, radium carbonate, things that you don't know that right now, you don't know what the thermal conductivity is, and you know that as a powder, they're going to be miserable to handle, but maybe not as miserable as handling metallic radium. So these options are opened by that. So that's where my present thoughts are. So at this point, we'll sort of wrap it up. And these few statements come from somebody else. The current supply of TAT radioisotopes is insufficient for even preclinical. Only a few research groups have access, and it's highly costly and a long waiting time. So therefore, it's important that we address it, try to find ways to do it. Accelerators would appear to be the most likely. However, the technical challenges are significant, especially production and handling of the radium targets. Personally, I expect significantly longer times before production of these things than present marketing would suggest. That's very common in me. I'm that way. More often than not, I'm right, unfortunately. Some of the participants, they just tear power, they want to do more melting of the thorium-235. If you look through it, long half-life means that every year about 5 milligrams of thorium-229 can be extracted from a kilogram of uranium-233, which remember is a bomb material, and requires 5 grams of thorium-229 to produce 1 curie source, which will have an equilibrium 1 curie with the 225 that you're interested in. So if you want to get 5 grams of something that takes 5 milligrams per kilogram of U-233, you're talking an awful lot of kilograms of bomb-grade material. So you're not going to be able to handle more than small quantities at once, and there's going to be an awful lot of processing. I don't know what the costs of it dealing with liquid waste, liquid alpha waste. I suspect it's not going to be cheap. So the cost of that approach are probably fairly high. Now, these other ones are now just basically from various websites. IBA is the cyclotron producer, but they're also producing those new Rototron 100 kilowatt electron accelerators. They've teamed with CEN in Belgium, and that's what they say. They're completing a feasibility study, and then they're going to the final design, blah, blah, blah. Groundbreaking expected in 24, production in 27. 2 years is probably a reasonable time frame to build a facility starting from scratch, I'm guessing. It's probably a bit optimistic, but certainly not, is in that right time frame. So that's their proposal. We have with this recent announcement of Chalk River that I TM in Chalk River to launch Accelerator as a joint venture for the global production. Triumph and the US DOE labs are producing it from distillation of thorium. They still need approval from the FDA for any drug that may be using that activity because of the problems dealing with actinium-227 contamination. North Star basically says that they expect to produce non-carrier added actinium-205 into 2024 and a drug master file. And since they canceled their Boeing 99 work, there's 2 accelerators that are already fully licensed and operational. So it might give them a value, but I've watched North Star's work over the last decade on other things. I'm not at all convinced because they have never met any of their promises that I've seen yet. So we'll wrap it up with that. So accelerators and reactors supply large quantities of medical isotopes, and it's done a lot of good. I mean, basically, the amount of misery that these isotopes have saved has been large. Reactors are aging and only a few replacements coming online. Cyclotrons have been a big part of the process for 50 years, and electron accelerators are new to the game. I personally expect the electron accelerators to play a more important role going forward, and that's because the big effort now, the exciting part of it is these new therapeutic isotopes requiring an accelerator to produce them. But again, it's likely going to take longer than advertised to realize any significant production. And with that, I'll wrap it up.
Bill is prepared to answer questions.
Right.
Try and keep it.
Just a comment in that you didn't mention that the only reason that electron production of moly has been possible because of the huge improvement in isotope separation.
Yeah.
30 years ago, a milligram of moly 100 was 20 bucks. A gram these days is 20 bucks. The surplus of centrifuges.
Yeah, they
really changed.
Moly is one of the ones that makes a hexafluoride, so you can separate it into cyclotrons. That's one of the big challenges in all of these things is, can you get the separated isotopes that you want? I mean, the U.S. program of using ion sources, the stuff that ended up from the end of World War II, they had these big ion sources producing many isotopes that could be produced only that way, but they closed, I don't know, 15, 20 years ago. There's no replacement. I think there's still some in Russia, but again, the chances of dealing with Russia at this point in time is probably pretty damn slim. So, but some isotopes are much easier to get at than others. Like the key isotope for copper-67 is, which one is it? One above copper-67. Anyway, it's produced as it's separated as an isotope because one of the ones in it is used as a poison in boiling water reactors. So there's a fair amount of that available at a reasonable price because of the design, interest from another party.
I just checked the internet this evening, and it turns out that moly, which 7 isotopes, is an organization that was promised 99.99% purity.
I know, it's ridiculous.
It's just amazing.
Yes.
John?
What is the cost of a single unit dose of the technique of
Well,
cost the patient?
8 or 10 years ago, when the last time I looked at it, the U.S. Medicare number was about $350, and at that point, the rumored number was that $350, maybe $2 went to Chalk River. So yeah, there was a large. Everybody on the line got a big chunk except us.
I can verify, I heard the same story at the same time. Alistair?
You've talked about the actinium-227 problem.
Yeah.
Are any of those routes going to really produce 225 on its own without the 227? Because that seems almost a deal breaker.
The electrons, because you're producing, the primary product you're producing is radium-225. So you're allowed at that point to do a separate, you give up a fair bit of yield. I mean, basically that first part you basically can't use for patient use. You probably use it for a number of research applications, but you're not going to use it in the regulated patient. But after that, when it grows in again, it's 225 without 227. And that's the only one you can get with that way, really.
You're doing a chemical separation.
Yeah, doing chemical separations. So it has a big advantage in that sense. There's a big push of the DOE down in the States to get approval for the spallation product, which is much easier to produce because they have the high energy accelerators, and thorium metal is very easy to work with as a target. You make coat it with something, and that's about it. You can hit it with pretty high photon currents. But again, it produces essentially almost atom for atom an actinium-227 for every actinium-225. It's just the difference in activity is difference in between 22 years and 10 days. So there's, but in terms of atom percentages, they're pretty close. And again, then you've got this part. Basically, the argument is that it makes no difference on the efficacy of the drug, but it's basically, I think one of the real big arguments is what do you do with the eventual waste that you start using this in large amounts? You're getting this alpha waste spread around. Peeing it down the sewer, all the rest of it. And I don't know, a lot of these heavy metals like that, I think a lot of them have high residence times in bodies, depending on where they stop. Things like leads and stuff like that.
I have a quick question.
Yeah.
How could you possibly use U-233 as a target material? Because it's next to impossible to use it in a reactor because it's got this very, very intense gamma that makes it.
Yeah, I know.
You can't go near this stuff. Yeah. How could you use it?
You're not using it as a target. You're using it basically as a separation. So you basically have to do chemical separation of that very small quantity of thorium-229 from a large quantity of uranium-233. But that large quantity of U-233 is limited by the fact that you want to be way, way below critical mass. And if I remember my criticality at all, I think a liquid is probably one of your worst situations for criticality, right? So I don't know what the volume of liquid with uranium-233 in is you have to worry about, but I suspect there's probably not a lot of 233 in there.
Maybe you don't want to, and I'll quit this point. You may not want to answer this, and I'll ask the people who in this room to keep this answer to themselves. But what would you say are the chances of Chalk River actually succeeding in this venture that they?
Oh, I would be significantly below 100%, shall I say?
By orders of magnitude?
We're going to use the Saskatchewan accelerator because they haven't got around to getting their own accelerator going yet. I don't know. I mean, I suspect that there's probably problems trying to find safety and licensing people who know how to do licensing for an accelerator. But that's just my seat of the pants feeling. But if I were Saskatoon, I would be questioning anyone bringing over something that's got a very large mass of radium in it that can get damaged and potentially make an absolute mess of my $25 million facilities. So I don't know how much, how much radium-226 you're going to have in your targets. I suspect they'll do maybe good R&D at that point. I'm not quite sure that, well, I don't actually know at all, but my suspicion as just a nasty little thinking physicist who's done a lot, has been involved in various things that didn't go right the first time or the second or third.
Well, thank you very much. I'd like to congratulate the audience who preferred to come here and listen to Bill rather than go down to the Legion and listen to the Beatles.
Yeah, we're similar age group, I suspect.